going to say, hey, Mike, don't forget to start the recording so that we don't ever miss a class. We've got to be about there. Let's check it out. I think it's official. Welcome back, everyone. So we're now finally on week number 2. I have quite a bit of announcements I want to get through just to refresh kind of things, stuff about quizzes, working in ALEKS, and so on, since we talked a lot on week 1, and we'll just give some reminders of important things on week 2 as we go. But before any of that, were there any questions that folks had at the moment? Okay, well, I guess my first big reminder is we have our first quiz coming due today. So the due date, I had to put in a specific time. I just put 2:30 p.m. That's when class starts, so it makes sense. But you are welcome to hand these in after class or before class. That's completely your option. And as another reminder on quiz 1, I don't have an option to collect it through the Moodle system, but if you worked on it digitally and you'd like to just send it to me, you can send it to my email directly. About 4 or 5 students have done that in class. So if you turned in your quiz by emailing it, then I'm going to grade it digitally, kind of like how we do our notes over here, and then I'll just email it back to you. So, I mean, there's a little bit of a perk to that. You get your graded quiz back faster. If instead you want to work more traditionally, I completely understand that. You can say, print out the quiz. You don't even have to do that. You can just open it, take out some ordinary paper, say like this, put your name on it, and just solve it, hand it in. So completely up to your option. If you sent in a hard copy like these, then I'll just be grading it and returning it to class on Thursday. Well, that's how each one of those quizzes are going to work. So it's going to be on the very bottom of the Moodle week that we're in currently. So when we come back on Thursday's class, you'll see quiz number 2. I'm going to keep them all kind of short and sweet. It's just a way to participate in the class and practice right away on some important topics. But any questions then, folks, about the quizzes? Yeah, go ahead.
I tried to ask this because online and it just literally said like problems and then like 2 hours later it said evaluate and there was really nothing else on there.
Oh, weird. Well, let me see. There's a couple things that could happen with that. So let me know if this fit your situation. If I click on this and then click on this, I get the PDF version, which usually prints a little bit better.
I can like open up the Word document. So
Gotcha. Gotcha. Yeah, I make the Word available since some people do like it, but I think it's more of an issue of, do you have like the most current version of Microsoft Word on your computer? If not, then it's kind of hit or miss, which is extremely annoying. So I'd say, maybe let me ask the class, has the Word file been beneficial to folks? Some people are using them. Okay, I'll continue to put those Word files just as long as some people like them. But yeah, I think the PDF is going to be the most reliable one. And also, this was just quiz number 1. If anyone's ran into any technology troubles and couldn't complete that quiz, I will be completely fine if you turn it in, say, on Thursday. It's only our first quiz. We're just figuring out how everything works pretty much. So if you didn't get a chance to work this out or get it printed out or so on, keep on working at it and I'll be happy to take it late on this one. But does that help out for accessing quiz 1? Awesome. Sorry for the technology troubles. It's always weird little issues we have to navigate through. Other questions at the moment? Okay, let's go back to our current course. And just a reminder on all these weeks that we're currently building, they're going to look almost identical pretty much. You'll see on the top of the week, the announcement will never be there, but it'll be the reading that we're going to be dealing with. The due dates I'll post after we complete a section, and these are the due dates for the actual topics in ALEKS itself. The PDF of the notes will always be posted there with the solutions, and the quizzes will always be at the bottom. So in our current week, we're really just redoing that entire process. Well, next thing I want to mention is, again, I want to just take another look at how things are going in ALEKS, looking at due dates and things like that. Any other questions or comments first? Yeah, go ahead.
So I'm on the last topic of 3.1
Mhm.
in ALEKS right now, and I was kind of struggling with that one yesterday. So that, like, if I had questions about it after class, I just talking about that and maybe work on it here.
Yeah, absolutely. I'm glad you mentioned that since something new does happen this week with getting help. I'm available after class by kind of a short turnaround. What I need to do is go to this room, CHE 220, from 4 to 5 p.m. So pretty much what happens is class ends, I take last questions, pack up, either use a restroom, take a break, and then I show up over there, usually before 4 o'clock, but no later than 4 o'clock. And if you have questions on your homework, Alex, working on a quiz, anything like that, those would be great times to hang out. Absolutely. Alex can be tricky. So yeah, if there's that one topic that has just been an absolute beast that you need extra help on, that is a great use of those office hours times. Monday and Wednesday, I'm in a different room, the tab building, but same offer stands. I'm just pretty much sitting there at a computer until someone comes and has questions so I can help. But other questions or comments about that? Okay, so these office hours are finally activated this week, and that's what my routine is going to be. Every Tuesday, Thursday, I'll just be there. You can email me to say, hey, Mike, can you help me with whatever sections? But you don't have to. They're completely walk-in office hours as well. Well, let's go to where we're just about at. Let me see here. There, so I've got to scroll right to that location. There we are. Next thing I want to talk about, just to help with a couple additional ideas with Alex, is every time we complete a section, I'll be putting these due dates on. So we're not quite done with section 3.2, but there's not much left to go. I'm pretty sure we'll have that finished off today. So I put the due date on it as well. This due date here, I may have to revise it just depending on where we end up with section 3.3. If we take a little bit more time with it, I'll push that due date backwards as necessary. So if we go back to the Alex site for the moment, here's about what it might look like once you log in. You might see something that says the Alex Pi right here. And I would say it's less important in all honesty. It's kind of cool watching each of these pie slices fill out. And notice they're in different shadings. The darker shade means it's something that I picked up on a knowledge check. I completed the topic and redid it through knowledge check, solidifying it. And the further line going way out here is the topics you've learned, but you haven't seen a knowledge check out on it at the moment. Really, that's all fun, that's informational, but it's not exactly where you get the points. If you lose a topic on a knowledge check, it's not going to bring your score down. It's all about completing these sections by the due date. That's where the points really are coming from the homework. So probably a better view here would be timeline. It focuses on what section you're working on. It says I have 8 topics left. What's coming up next? Section 3.2a, prep, section 3.2a, and then same for 3.2b. And so I think it's a better screen if you just click on timeline here. Completely up to you, but that's my take on that. Any questions or comments about this view right here at the moment? Yeah, go ahead.
Whenever I was doing the Alex earlier, I finished the 3.1a.
Yeah.
And it seemed like since I had taken a break in between 3.1a and 3.1b, I had to go back and stuff with 3.1a again.
I think it might have been the prep that was having you do. There's a prep for 3.1b as well, which had some topics that might have felt like the other prep topics.
Because it said 3.1a as a section.
Mhm.
I finished all the topics for it, so I wasn't sure why I was saying that again.
3.1a right here.
Yeah.
One thing it could have been is if you click on this menu bar, there's another thing here that says review. And if you do review topics, you could go backwards visiting prior sections. This is dangerous though, because if you click on review and we keep working these problems, we're not actually making progress on the current assignment. But I'm not too sure if that was the major issue there. We go back to home.
I was just a little bit confused about it because it did show that I had completed all of the topics, but it may have been left over from the actual assignment and not because I didn't realize that there was 2 sections.
Possible, yeah. It really started off with 4 different sections all at once. 3.1, because it was a little bit of a longer one, the math department broke it off into 3.1a, 3.1b. And that prep section was some topics that you might have been a little bit foggy on after the initial knowledge check that Alex decided were supportive to 3.1a, 3.1b. So there's really 4 things to get through on that first one. So yeah, it's a bit confusing to start off for sure. Does that help out with the question there? Gotcha. Was there a comment or question here?
I was that question, so I did all the like 3.1 stuff, that was all we made, but then it showed the 3.2 stuff,
Mhm.
but I was just, I guess verifying, it's showing his due date as Friday, and I was just wondering if that was the case, or that was a quicker turnaround than the two prior sessions.
Yeah, that was the case for that one. Yeah, I put out a really long due date because we really took us a while to even finish 3.1. We were just getting started. And it was a longer section with a part A and part B. I think that might be true with 3.2, but it's a little shorter. Yeah, yeah, a little bit shorter. But yeah, the due date for that one was intended to be Friday.
Okay.
And again, the due dates are kind of in flux. Here's September 1st, Friday for that due date. But again, if we needed extra time to finish section 3.2, I would move that so we have ample time to get through. Does that help with that comment question there?
Yeah, I think
Yep, you betcha. Other questions so far, folks? Okay, now I was mentioning I'm going to be doing this along with the class because I haven't done ALEKS since 2019, and I just think I need a refresher. It's a kind of a tricky system to get through. So I'll be mentioning topics and tricks and things like that at the start of class here and there. But one of the things I'm going to be doing for Thursday is I'm intentionally going to let this go overdue. It's due today at 11:59 p.m., but I'll let it go overdue to show you what does that look like on Thursday and how to get extensions to continue to work on those sections. Does that make sense so far? Okay, so definitely don't do as I'm about to do. Definitely complete section 3.1A and 3.1B, but if life gets away from you and you need to revisit a section, we'll be discussing that on Thursday's class. So there's no penalties for not finishing it on time. Think of the due dates as a really good idea to complete them by the due dates for the sake of pacing. So you're not getting inundated by the time exam one comes around. If you're completing everything by the due date, then you're going to be in really great shape for exam one. Well, any other questions at all, folks, before we close out ALEKS? Okay, so the short of it is the sections you're working on are on the left. Pay attention to the due dates and anything about the time goal. Well, that's also just for pacing. You're not getting any credit if you don't meet your time goal. It's just a way for you to decide, did I actually work 3 hours, less than 3 hours, or more than 3 hours on any given week? The average student would do about 3 hours a week for this class. Well, let's now go back to where we've been leaving off. A lot of announcements on the first couple of weeks, but that's kind of normal. There's a lot of information to get through to see how the class is going to run. And let's see, we talked about the quiz. I'll always say where we're at, so you can turn to the right section of the notes. But I did have another question in class when we were doing some problems involving absolute value. So let's start off class today with this review problem right here. Occasionally, I will just throw review problems on Moodle. So if you're in class early and you're just really bored, give it a try. And then when we do it as a class, you can check your work, see how close to target you were, things like that. So here's how I'll typically do it. Let's just steal the review question. So this actually saves. And I'm going to put it inside the notes between example 1 and example 2. So we're right here. Okay, so let's start off with this question today. The reason we're doing this review question was, it was really a question earlier about, is there an absolute button key on the TI-30X2S or the TI-30XA? I researched that, and sadly, the answer is no, there's no actual absolute button key. But it's not too bad to evaluate these, so let's practice anyways. Let's say you were using a calculator. If I want to evaluate f of 2, we go to the function definition, write out f of 2 equals -7 times the absolute value. Anywhere you see x, like by the red dot, I'll put a placeholder with parentheses, put in the 2 and square it, -8. So all I've done from the original function is plug the 2 right where the x was, raise it to the power 2. And this was not too bad to just go through an order of operations. Let's do that, and then we'll double check it in a calculator. So it becomes -7, absolute value of 4 minus 8. So all I'm doing is working on the inside. Inside here, I'll get -7, absolute value of -8. And then finally, last thing that happens is well, almost the last thing, absolute value of negative 8 just forces it to be, well, let's fix that. That should be a -4, right? Let me get that corrected right here. You can tell I miscopied something. Folks' eyes look like there was just something wrong. So always direct me if I miss something or my arithmetic goes sideways. It's really good to get it definitely right. Because this goes to YouTube, it's saved forever, and that'd be a terrible mistake to just let fly. But now we take the absolute value of -4, it becomes positive. So -7 times 4. And the whole answer becomes -28. So we did that completely by hand. Any questions so far, folks, on that answer there? Okay, yeah, go ahead.
I- How will the extra value for use the
Visually, this is what the absolute value function is really doing. We go to the number line centered right at 0, and we take our input of -4 that was coming from right here. And all absolute value is really going to do is count the distance from that -4 to the number 0. Since the distance equals 4, that's the value that we plug in right exactly there. So the end of the day, absolute value, it's really just peeling off your negative sign. Any number you have inside here, if it's a single number, no other operations, is force positive. Yeah, go ahead.
So, well, it's like it becomes positive because you're moving to the right, you're moving in a positive direction. So like if you're on the other side of it, it's 4, the distance 0 from +4 is going negative direction to 0. Is that the idea? Whether you move in a positive or a negative direction?
It wouldn't matter either way. Yeah, it's always just the distance, not,
So like if it's +4?
it would still be
stay
4.
+4?
Exactly, yes. Yeah, so if we had, say, 4 right here, we would still say distance equals 4 and get an absolute value 4 altogether. Other questions about that so far? Okay, so finally, other thing I want to bring up is if you were to try to put this into a calculator, now I don't have a TI-30X2S that I can really show. I don't have an emulator for it. But if I was to type everything inside here, this is about what it would look like, even in that calculator. I can't put in the absolute value function right here, but we can instead just put 2 squared minus 8. We get a value of -4. Then if we want the absolute value, we just convert that to +4, like where the red dot is, multiply by -7, and we're getting our answer of -28 altogether. So even though I can't throw in the absolute value function, put everything inside in your calculator and ignore the negative sign, and you've got the right answer. Does that make sense to everyone so far? Awesome. We'll be working with a lot of strange functions, and the more we learn about functions, the more we learn things like absolute value are really kind of weird. For example, if you wanted a formula for absolute value that you might be able to put in your calculator, it is kind of overkill, but it looks like this. The absolute value of any real number A can be defined as the square root of A squared. So that's a random formula that our book hasn't discussed. That's why it's putting in orange. But you could do absolute value like that if you really want to. Probably not worth the effort. It's kind of overcomplicating it at that point. Yeah, go ahead.
Why do we use absolute value?
That's a good question. Let's see. I would say some functions, like, for example, a nice function like square root of x goes like this. So it's a fine function. The larger the number you put in here, the higher this curve is going to get, but it has some issues. If for there's some reason you want to put, say, a -2 inside your function, maybe it makes sense for some reason. Negative numbers have to go into your process, and it's still going to be a square rooting. You couldn't actually put a -2 inside there. We'd get a non-real number. But if you put absolute value inside there, now you can. You can throw in your -2 right inside here and get an answer out. So that's going to allow positive and negatives. And now we have a new function that goes like this, going in both directions. So sometimes we just need to add a little bit extra to our function to achieve, say, negative values if necessary, and along those lines. many, many other reasons, but I'd say that's my go-to explanation of the value of it. Other questions about that? Okay, well, let's go next to where we left off on. Before the review question, we were dealing with domain and range. And the short of it was, the domain is a set of all horizontal values, all the inputs that you can throw into the function. And the range is a set of all the vertical values, the outputs, the second coordinates that can go inside the function as well. And we had to end class right after this one. So how about we try this again, or example 2. So that's where we're at currently. And with the same instructions, we have a brand new graph here. Let me make it a little bit bigger. It says the entire graph of a function f is given below. And we're going to do this, write the domain. I'll do domain in green. And range, I'll do in blue, using interval notation. And the first page of this note is really just the review of getting that interval notation down pat. So again, we think of the domain as being all the possible inputs coming from the horizontal axis that can actually go in the function. But what's new about this function is the arrowheads. This one's a nice parabola, so the arrowheads just say it's continuing off in that direction forever and off in that direction forever. And as it continues down, it also is moving to the left. Would you all agree with that? That means it's moving to the left forever. And even though I can't put in a -10, if I could scroll down far enough and drew the curve far enough, we'd eventually hit the graph. -10 wasn't special. You can go to the left to any large negative number, and it will work as an input. Likewise, anything on the positive end you can input as well. So we can say here, if that's the case, domain is this set from -infinity to +infinity. In other words, all real numbers would qualify for that domain. Does that make sense to folks on the domain for this one? Okay, so think of domain, you're worried about what are the positive or possible x-axis values. Now for range, this one's a little bit trickier, I'd say. Range wants to know, what is the possible output values? Well, as we take any single point here, let's say on this one, an output value would be -4. Go somewhere else here, here's an output of -6, and everything intermediate is obtained. And it just keeps on going down, right? So it looks like any large negative number is possible here, but not every large positive number is possible. There is nothing that goes with, say, a 7, because the curve never goes to that height. If that's the case, any volunteers for what the domain, or excuse me, what the range should be on this one? Yeah, go ahead.
-infinity to 4.
Exactly. Now, when we go up to 4, remember, we have to be really careful, right, with those brackets and parentheses issues. We did on the, oh, good call, brackets are integrated. We did on the last one, we had ability to sort that out a little bit nicer. Because in this last problem here, the open circles corresponded to a parenthesis, and the closed circles corresponded to a bracket. But this curve didn't have any of that. We just had to know that, yeah, that is a point on the graph. That's the highest one obtained. So it went up to a height of 4 at the very, very highest. So we did it, folks. For this particular graph, domain is all real numbers, but the range, it only goes up to 4 and then it stops because the curve has a maximum height of 4 until it comes back down again. So even though it's a simpler looking graph, I think this one is just as tricky in example 1 until we start getting a handle of these weird little issues here. And to me, this was the trickier thing right here, leading to the bracket. Any questions at all, folks, on example 2? Yeah, go ahead.
So the brackets being used for number 4 because that's where it stops. Basically, it doesn't go entirely down.
Exactly, that's right. Other questions? Okay, so this is domain and range given right off a graph. This gets a little bit tricky if there's no graph at all. Sometimes all we have is a formula for the function. That's what's happening here on example 3 with the so-called domain convention. So let's take a look at the convention and then give these problems a try. Convention says unless otherwise indicated. The domain of a given function, y equals f of x, that's what we have here, the f of x portion, is assumed to be the set of all real number inputs x that lead to a unique real number output y. There's a lot being said there, right? So let's track through this definition and see how it all goes. I want to highlight this portion here. Input x that leads to unique, that gives us a function. Real number output means we're trying to avoid something like this. We don't ever want to deal with, say, the square root of -1 in this context. This is the imaginary number I. We'll have some to say about that once we're in the further chapters. But for the moment, if we're just talking about functions, we're not looking for anything like this. That's to be avoided. Well, let's start off with example 3. It says find just the domain. That's all we're trying to go after on all these functions. We'll state the answers using interval notation. And here's how this one could go. It's a square root function. So first, let me go to this pen. If you see this orange pen, usually it just means it's scratch work or it's just an additional comment, not really part of the full solution. What I'm trying to do here is get a feel for what can I plug in. If you tried, say, putting in 0, that's an input x I'm trying to throw into the function. But f of 0 would mean 0 goes right where that x is. And it becomes square root of -4 once we do the 0 minus 4. But that right there is not a real number. And that means 0 as an input doesn't work for this function. It's not in the domain at all. So one of the things we have to do before we even get started is wonder what are the problems with the function that could lead us to not having a unique real number output y. And here the big problem is there is a square root. Any even root, if it was a 4th root, 6th root, or so on, can cause a problem. So here's the big takeaway on this one. This is a square root. Function. Once you notice you have a square root function, the work really boils down to just this. We take what's inside, x minus 4, and if we're having trouble with negative values, we just assert x minus 4 had better be non-negative. So I'll set it to greater than or equal to 0. That's what we require to get the right domain here. Next thing we do is we just solve for x here, add 4 to both sides, and x has to be bigger than or equal to 4 exactly. Any questions so far, folks? Okay, that means we're essentially done. This is the domain in its inequality form. We want interval notation. So just a reminder, if you need some practice doing that, or if it's getting a little tricky in ALEKS, take stuff that looks like this, go up to what this is meant to be as a cheat sheet and find the one that fits. X greater than or equal to 10 looks like that, bracket 10 off to infinity with a parenthesis. So an interval notation, based on our practice work from before, it turns into this. Sorry, question first?
So the square root, so x minus 4, is that solving for the range? Is that why you highlighted that?
Oh, no, we're just solving for the domain.
Okay.
And the thing inside had to be positive. So that's why I highlighted that portion.
Okay.
Other questions at the moment? Okay, so we'll go here with x greater than or equal to 4. We can now say domain is starts at 4 and every real number thereafter. So bracket 4, comma infinity gives us the domain on this one. So that's why f of 0 didn't work. You're getting a negative number on the inside where it's highlighted in blue. If you plug in 4, no trouble. Root of 4 minus 4, that's just the square root of 0. You get 0 right back. Plug in any other positive number, you'll get a real number back. And so that's the full domain. Any questions at all, folks, on getting to that portion? Okay. I would say part B is definitely a little bit trickier. Now, it's not a square root, it's a cube root, but let me take this, and sometimes it's hard to see those little 3s. If anything's hard to read, let me know. I'll always blow it up immediately. But this one's a cube root. Cube roots are special because you can plug in any real number whatsoever. It actually doesn't matter. In fact, let's test it out just with a calculator, just to get a feel for it. In this particular calculator for Desmos, I'm just going to redefine the whole function. G of x equals, I need a cubed root, but the way to do that is to start with the parenthesis, even on the TI-30XA, this is how I'm going to do it to cube root, plug in 2x plus 4, and then raise this to the power of 1 divided by 3. So that's going to give us the entire function. And down here, we can try g of, say, 5. If we plug in a positive 5, we get a 2.41. We can try negative 5. We get an answer out, negative 500. That's all totally fine. And what's making this work, every input is giving us a unique real answer output, is the fact that that's a cube root. It's odd. If it was even, if it was a square root, here, this would be 1/2 instead to correspond to the square root. And notice it says undefined immediately. It's because a negative went inside. So really the big takeaway for this particular function is, if you see odd right here, then this is an odd root function. And that deserves an exclamation mark. And here's the reason. Any odd root function, whether it's a cube root, fifth root, seventh root, has this fact. Domain is all real numbers. So negative infinity to positive infinity. So these are like the freebies when you see them in the actual ALEKS system. But if you see something like this one, well, you grab the portion inside highlighted blue, solve an inequality, and then it gets you your domain. Well, that's 2 down. Any questions at all, folks, before the next? Okay, so we had a square root function. Next, we went to a cube root function where everything's fine. It has the world's best domain, all real numbers. And now this function is different. We're later going to call this a rational function. I never liked the word rational, but it's in math, so we just deal with it. It doesn't mean you can reason with the function. It just means it's a ratio of 2 other polynomial functions. Polynomial on the top, x plus 8, is degree 1, so it's graphed as a line. Polynomial on the bottom, 2x squared minus x minus 3. That one's quadratic, so it would plot like this one, except it would be opening upwards. Its graph would look about like that. But this entire function itself, it's going to look really wild. We'll have an entire section on plotting those kinds of functions to get a feel for it. But for the moment, here's what can go wrong here. If we have 2x squared minus x minus 3, we still have issues where you cannot divide by 0 on this thing. So we have to wonder, in what ways would you divide by 0 if you could plug in that number? So let's add here, for a rational function, the instructions are set the denominator equal to 0 and solve. Now, this isn't finding the domain, it's finding the opposite of the domain. That's what's a little tricky. If we do those instructions, we're solving for all values not in the domain. So we'll have to state the domain right after. Let's make that an important note and solve to get all numbers not in the domain. So that's our goal here. Now that we know we have a rational function, we just have to navigate through it. So where's the denominator? It's this thing, 2x squared minus x minus 3. If that ever becomes 0 for a particular choice of x, that choice of x is not in the domain. So now we're hunting them by solving this. 2x squared minus x minus 3 set equal to 0. Kind of a root equation, but part of our objective here is just to refresh ourselves on how these ought to be solved. Because the power is higher, it's of degree 2, you could use some really powerful tools on this. Say the quadratic formula we'll discuss and use later on. But probably the tool that's going to work the best is just factoring. This one factors really nicely. as a product of two binomials. So first thing we're going to look for is what should go in the first slots. That's all about splitting off the 2x squared. I need to multiply two numbers to get 2x squared, and 2x and x would absolutely do the job. So essentially, we're producing an answer so that if we were to FOIL this answer, we get the result above. Some folks might be a little bit foggy on it, and if it's been a while doing this, no worries, we'll be practicing it quite a lot. Next thing I would focus on is, well, I wouldn't scribble on it. Let me try one more time. I want to figure out what should be the signs in the middle. Anyone see what they should be? Plus, plus, minus, minus, or mixed? Exactly, because of that right there, signs are opposite. Now, I don't know exactly where they should go, plus, minus, minus, or plus. There's exactly one answer. And this is trial and error, so I'll just put down plus, minus. If I'm off by a sign, I'll just change them around. So pencil is a great idea for this, or just scratch paper. I'll just try with the plus and minus. I'm going to leave it in orange because I may have to change it. Now, last thing to do is, to get that 3, I need its factors. The good news, it's prime, right? So 3 by 1 is a really good choice. And if I put, say, a 3 here and a 1 there, it may or may not be correct. The most important thing is to now check our answer and see how close we are. Well, the check that I do is going to be based off of this. I already know if you multiply here to here, that's 2x squared. We're good on that. And we already know that if you multiply positive 3 with negative 1, you get a negative 3. So we're also good on that. The only thing that's undecided is the negative x. But that's going to be this product, the outer, and this product, the inner. If those both multiply and give us a negative x, then we have the right factorization. If we're off, then we'll just change something small. So let's take a look. 2x times negative 1, that gives us a negative 2x. Then 3 times x, that gives us a positive 3x. Now we add 3x, so let me put it here, minus 2x to give just positive x. And that says, is our work right or wrong? It's definitely wrong, right? Anyone see what we have to change? Flip the signs, it should go minus plus. We don't throw away the 3 here, the 1 there. It's in the good position. We just need to go, as you said, minus plus. It's trial and error, so we're just zeroing in on it as we try to get to it. So here, negative 3 by x is negative 3x. 2x by positive 1 is positive 2x. So we're taking a negative 3x plus 2x, and that does give us the negative x. So back up here, that means we have the full thing. It really is the outer arrow way out here to here and the inner arrow here to here. That's most fundamental in the check, but no harm in just foiling out the whole entire thing to be extra sure if you wanted. Well, we did it, folks. That's the process of factoring that. How does that feel to folks? Kind of rusty, not too bad? Okay, if you do feel kind of rusty, you can ask me and I'll be happy to include some review problems on factoring methods, but we're going to be practicing them as well as we go through the course. But let me clear this off. And this problem is turning into a long one, right? So watch out for the rational functions when you see them on this topic. Let's review what we were doing because we have lots of things going on. We want the domain. The domain is going to be the largest set of input values x so that we don't divide by 0 in this rational function. So we took the whole denominator, set it to 0 and say which x's result in that. The reason we want factoring on this step is the 0 product property comes and saves us. We have two things multiplying resulting in 0. And the only feasible way that ever happens with real numbers is if one or the other was 0. So you take the first thing, 2x minus 3, set that to 0, and the second thing, x plus 1, set that one to 0, solve them both, and those are going to be the excluded values, which are not in the domain. So we'll have x equals 3 halves. On equation 1, I just added 3 divided by 2. And the other possibility is negative 1. Just subtracting 1 from both sides. So those are the values which are excluded. Any questions or comments so far, folks? Okay, now our end answer is going to be an interval notation. And it wasn't too hard to do in part B or even in part A. I'd say this one's a little bit tricky. So I'm going to include an extra step here that you don't have to write in, but if it's helpful for you to get interval notation, it might be a strategy you could use. So to nail the interval notation, I'm going to just draw an interval. And the idea of what I'm doing is I'm trying to get back to this kind of stuff. I know what the graph looks like. Interval notation is just paraphrasing the graph. It's extremely fast to go from one up to the other. So let's just take a look at what the graph would look like in this situation. We're cutting out two values on the graph, 3/2 and -1. So I'm going to shade in a way that looks like this. Here's -1. Here's 3/2. I'm going to put open circles on them to say we're excluding those values. And everything else is going to work. So I'm going to shade the number line like this, going left forever towards -infinity. Shade in the middle, that's going to work. All the numbers between -1 and +3/2 are also valid. And every number greater than 3/2 also works. Off to infinity. So finally, our answer would look like this. Domain is, we're going to read this going left to right. First, I have -infinity, and that has to have a parenthesis adjoining it. So -infinity with a parenthesis, then comma. We go up to a -1, but you can't throw in a -1, so another parenthesis to exclude it. Now go off to the middle. All numbers between -1, 3/2, they work. So we'll say union -1, comma 3/2. Then skip right over here. From 3/2 off to infinity, all those numbers are valid as well for the domain. So we'll say union, the last set, 3/2, comma, infinity. So finally, that's the full domain. We had two excluded values, and this is essentially what's saying. Exclude -1, we skipped across it. Exclude 3/2, we skipped across it as well. Sad thing is, if you exclude two values, you've cut up the real number line into 3 pieces, so it takes a while to write all that stuff down. Well, any questions, folks, on getting through this last one? Okay, so if you're dealing with domain and range, or excuse me, just domain for these kinds of problems, and they're just throwing equations at you, try to classify it. Could there be a denominator? Is there any way for that denominator to equal 0? That's one way to find the domain. Watch out for things that look like, say, a cube root. That one's the freebie, all real numbers. And for square roots, you have to solve an inequality to get the right domain. So you could come back to these notes to see the process, but if you see a tricky one, don't hesitate to get help from me. I'll be happy to help out. Well, any questions at all, folks, on getting through these here? Okay, what made this tricky is there's no graph. And what we're going to do on the next ones is, well, there's still no graph, but we're going to graph the function. If you know what the graph should look like based off information on the function, then you're not able to just get the domain. You can also get the range pretty easily as well. So we're going to try this out again, but this one is more of a review for us on some graphing techniques we should be aware of. Any questions before we start it out? Okay, so do domain in green again, just to keep that similar. And range will be in blue. And just as a reminder, range is going to be all possible outputs, and the domain will be all possible inputs. So let's give this a try. First thing we want to do is graph this function. And let's see, it's y equals -3/2 x minus 1. Special thing about this function is it's linear. And graphing a linear function is not too bad. You just need to grab its slope and its y-intercept. So we'll start with that step. I'll write m for slope, but let's say it here. Anyone see what the slope would be equal to in this function? Exactly. It's this leading coefficient right here. Ignore the x isn't part of it. The slope is just a number. So -3/2. What that slope tells us is, if we know one point on the graph, you can get to another point just using the slope. You have to go down 3 and right 2. So it gives you instructions on getting a next point from a known point. Now we need to find our known point. That's the next step here. And the thing that this format gives us is the intercept. If it's a y equals and the degree on x is 1, the exponent is 1, then the y-intercept is also given. I'm going to write this as an actual point, so a set of ordered pairs. The first coordinate, if you said y-intercept, is always going to be 0. Anyone see what the second coordinate should be then? Exactly. And you really didn't have to do anything, right? It's right here. It's looking at us. But if you did take this 0 and you did plug it in right here, you're still getting -1. -3/2 times 0 wipes it out. And that's how you get your y-intercept no matter what, even if the function was more complicated. But linear is great. It's just -1. It's that last coefficient there. So now we have everything. We have an initial point, 0, -1. We have directions to a next point. So we're going to be able to plot this really fast. Then we'll say what the domain is and what the range is. Any questions before we go to those last steps? Okay, so here's what the motions are. If this was an exam question, I'll print actual graphing paper right on your exam, so you don't have to worry about details and artistic talents and things like that. But as long as I can tell what the points are on your graph, it doesn't have to be perfect. It can be a little rough. First thing I'm going to put in is 0, -1. So that would emerge right here, -1 on the y-axis. Now from that point, we first go down 3. So here's 1, 2, 3 tick marks going down, and right 2. So 1, 2 tick marks going right, and we end up on this point. So it's good to double check. 1, 2, 3. So we went down 3. 1, 2. So yes, we went right 2. Now here's the toughest thing about this. I need to draw a straight line, and strategies are, if you start at one point and just head towards the other, sometimes it works out, but not always. It looks like I did okay here. And then I'll just extend it off going that way. It got bent right there, but we'll just interpret that as a perfectly straight line. Well, we did it, folks. We have the graph. Next thing is domain and range. Any questions on producing the graph so far? Okay, so next, going to domain. Domain is all the horizontal inputs that you could possibly put in, all the x values. But notice the arrowheads. It's going to the left forever. It's going to the right forever. It's kind of like example 2 we started class with today. In this case, domain is all real numbers immediately. Does that make sense to everyone on this one? Awesome. Any volunteers for what the range should be? Exactly. The range is all the possible second coordinates, all the outputs. But if the graph is going up forever and down forever, it's also all real numbers. So range equals -infinity to +infinity. And if you have something that looks like this with a non-zero slope, a line that's not horizontal, there's some bend to it. This is always the case. Domain is all real numbers, as is the domain. Excuse me, as is the range. If it's horizontal, your domain will be all real numbers, and the range would just be the one number, which is the height of the line. Well, any questions, folks, on this one? Yeah, go ahead.
I did have a quick question about y-intercept.
Mhm.
-1 that we had with y-intercept was
Yeah, which went to right here.
the 0 pointing back to the
Well, it'd be from right here, really. The coordinates of the y-intercept are at 0 for x and then -1 for y. You could have just said y-intercept equals -1. That would have been okay as well. But our book and Alex as well typically writes the whole point. So 0 goes in first. Other questions about that at the moment? Okay, so that's graphing a line. On this next one, we're graphing a parabola. We have an entire section on that, so this one feels almost kind of unfair in a certain way, but really it's not too bad. I'm going to plot this one the way that Alex has us do. We're going to just plot some points that are convenient and see what the whole graph looks like. So we'll be getting into more of these kind of plots later on. What makes it different is, let me blow it up a little bit. That power of 2 right there makes it nonlinear. This one's a quadratic. So if I'm going to plot a quadratic, and I'm not trying to use any of the fancy techniques that are later on in the book, this would be a great way to start. An x-coordinate and a y-coordinate. The y-coordinate is going to be the output of the function 3x squared minus 4. All I'm going to do is plug in convenient values and then just connect the dots. Does that make sense to folks so far? Okay, so it's the good old point plotting method. And what's nice about it is no matter how convoluted that function gets, if you can plot points, you can probably obtain a really fast graph. So let's start off with maybe the world's best input to 3x squared minus 4. How about a 0? But you'll agree that'd probably be the most convenient input ever. It just makes work fast. There's no reason to torture ourselves with weird numbers. So start with a 0. 0 goes inside, it's 3 times 0 squared. So the whole result is just a -4. Now, I'd say the next most convenient value might be a positive 1. If we throw a positive 1 here, it'll be 3 times 1 squared. So it's just a 3 minus 4 altogether. That means we'll get a -1 on this one so far. And then how about one last one, a positive 2. Notice when I put in a 0, that was the easiest one to use. We're going to later call this first coordinate to a vertex. And my next values, I'm not trying to go too far away. I'm just very timidly going 1 unit off from that easiest value to plug in. And already at 2, let's work this out carefully. Here's what we get. I'll put it as scratch to the right and then plug it in where it should go. We'll have 3, 2 squared minus 4. So it's going to be 3 by 4 minus 4. So 12 minus 4, which means we're already up to 8. If I put in a 3, I'm off the page all of a sudden. These kinds of functions can grow really, really rapidly. But this should be enough for us to work with already. Any questions at the moment? Okay, there is actually some freebies here. I made my table just a little bit longer. Here's what they look like. I'm going to use just a slightly different color pen. So that power of 2 is kind of nice for us. It's giving us symmetry on the actual graph. And here's what I mean. If instead of a positive 1, you put in a -1, -1 would go here and you'd square it. But -1 by -1 is still positive 1. It's 3 minus 4. And you repeat a value of -1. That wasn't a coincidence. If I go 1 to the right of 0 or 1 to the left of 0 at -1, I'm repeating that output. Let's try it again. I put in a -2. -2 goes inside here, but when you square -2, say that's what the work looked like, it's still a 4 right here. It's still 12 minus 4, and you still get an 8. So values repeat on this, and that's really helpful. It means I just focused on these points. I can reflect them and get the other points all together, or just list them out, and let's plot all 5. Well, any questions, folks, before we actually plot them out? Okay, I'm going to erase this since it was mainly just scratch work in producing these values. And now here's what the graph is going to look like. I'll indicate in red where I'm at. First point is 0, -4, so I'll go down 4. There's our first point. Then we'll go 1, -1, so that's going to be right here. It's already gained a lot of altitude moving over a little bit. Next, it's 2 at the height of positive 8. So 1, 2, 3, 4, 5, 6, 7, 8. So here's that next coordinate. And this is not a straight line. It's going to be a parabola that's fairly narrow due to the leading coefficient of 3. And it would look about like this coming in from the left. Trying not to draw a straight line could be tricky. Let me zoom in and see if I can do a bit better. Okay, so it's gonna come, oh, that's the eraser. Control C will help us there. It's gonna come in and increase in about that kind of way. Now, like I mentioned, there's a bunch of symmetry here. So I can reuse these values. At -1, I'm at height -1. So here's -1, -1. At -2, we're at height 8. So here's -2 at height 8. And here's the rest of the graph coming in this way. Notice I missed a point. If that happens to you on, say, an exam or a quiz, I'm not going to be super picky on that, but there is a strategy here. Make the point bigger and no one can tell, and that'll be completely fine. Well, we did it, folks. That's a rough graph. I have a shaky hand, especially on this technology here. But if yours looked even a little bit worse, again, it's always for full credit. I'm not too terribly worried about that. Next thing we want is just domain and range. Any questions at all first before we give it a try? Okay. Well, as we solve this one, remind yourself that it's really just another version of this, right? Instead, we had to plot it from scratch. The arrowheads are helpful because reminding us it's extending to the left and to the right forever. So the domain is still the same. In fact, any polynomial function will have that feature on its domain. So here, we'll just say domain equals all real numbers. So from -infinity to +infinity, and now we're all set. But it's the range that was a little bit tricky with these. So let's do this one very carefully. Range is the set of all possible outputs to the graph. Now there's no outputs below here because there's no actual point on the graph. I know that this is an output because it corresponds to this point, and to the left, that point as well. So anyone see what the range should be? All the possible outputs? Absolutely, bracket -4, and then exactly. So I like the way you said that. Whenever we're doing the range, we're on the vertical axis, and we always go from bottom up. We start at -4, so bracket, just like you said. And because it goes up forever, we just cap it off with an infinity. There's no upper bound on that range there. So that's domain and range saying yet a different way through these particular graphs. Any questions at all, folks, on getting through these? Okay, well, we're nearly done with these notes. Sections 3.1, 3.2, they're a bit of a slog to get through since college algebra is an interesting subject, and it's really just focusing on functions, function notation. Loads of little machinery and things to keep in mind for that. So the whole course won't be necessarily just like 3.1, 3.2. Some of these sections are a little bit shorter. I threw in a couple more topics on these just to help out with the homework. I noticed there was piecewise defined functions, so this kind of stuff. So on example 5, we'll just practice evaluating this function. And then we'll do it again on example 6, except we're going to plot this one. So let's try now piecewise defined functions. The reason these kinds of things are called piecewise functions is the actual definition for the function g of x, it depends. It depends on, is x less than or equal to -2? Is x between -2 and +1? If it's here, that's the function definition. And if your x is greater than or equal to +1, the function definition turns into this thing. So kind of an irritating function in all honesty, because we have to pay attention to the domains right here and the right function to pull in. So let's practice just by doing these evaluations. I'll go with these 3 colors. There's a domain here, and a domain here. So on the first evaluation they ask us for, g of -8, the first thing we have to decide is, where does -8 belong to? The purple, green, or blue domain? Anyone see which one it has to be? Yeah, go ahead. Exactly. The -8 only qualifies to this right here. So now that we know which one we're going in, we get to use that function format here. So it's all about spotting where you're at and getting the right detail. So this is going to turn into -1/2 parenthesis for x plus 2. We'll throw in the -h right here. And then just evaluate. Does that make sense to folks on how to start these out? Okay. From here on out, it's not too bad. The two negatives cancel, 2 goes into 8 4 times, so it's 4 plus 2. And we get a result of 6 on that one. So that's all well and good. Let's try this again. On the next one, we're doing g of 0. So now we take a look. Where does 0 belong? Not going to be in this set. 0 is larger. Sorry, go ahead. Exactly, but 0 belongs to this set right here. So that means this time we're using that function definition. There's a sudden switch to what the function outputs from one part of its domain to the next. So now that we've indicated what function we're using, we'll write this in as parenthesis for x, -1, big parenthesis for everything to be squared, then -3. Meant to highlight that as 0. Throw 0 right inside here, and now we're ready to go. So that's our second approach. And these are kind of fun in a certain sense. You just have to know, where do things go? The input values correspond them to the right-hand side, and then you grab the function like we're highlighting here. Make sense to folks at the moment? Awesome. Now let's just crank it out. 0 minus 1 is just -1. So this becomes -1 squared minus 3. The square of any number is positive. So this becomes -1 times -1, +1 minus 3. And the whole result settles down to -2. So now we have our value. Well, that's 2 down. And notice one thing I did, which, maybe it wasn't the best thing. I maybe should have scrambled these. That might have been funner, right? G of 4 goes to the last one. But I'd say if you do these in ALEKS, they might be scrambled. The first one doesn't have to be the first domain and so on. But now let's go off to the last one, G of 4. You can't put a 4 here. It doesn't solve that inequality. 4 is not between -2 and +1. So instead we go to that last domain. X greater than or equal to 1 does work for 4, which means we're using that particular function. So let's write this out. G of 4 now. We've identified the right function in blue. So it's going to be equal to 1/4, a parenthesis, -2. Inside here, let's throw in that 4. And that's about done, right? That becomes 1 minus 2 for overall value of -1. And now we have our answer. So that's how to evaluate with these kind of problems. And this is one entire topic itself already in ALEKS itself. It's not too bad until we see just how to grab the right piece. Any questions at all, folks, on getting through this one? Yeah, go ahead.
So with knowing which G value to point in, you just have to refer to the if section and see if that number fits the criteria, what's in that if section.
Yeah, exactly. So it always starts, essentially, if we think of this as arrows, we start here, we pick that, and then we take our 4 and throw it inside there. So as a process, that's how it goes, exactly. Other questions at the moment? Yeah, go ahead.
So as long as it's all correct, none of the if statements should overlap.
Exactly. If they did overlap, then the question would have been poorly written for sure. It would be an invalid question, essentially. And I like how you mentioned that, since notice also the equality signs. This is less than or equal to, that doesn't actually compute. Let me try again. This is less than or equal to -2. And so when we come down right here, that should be strictly less than. Otherwise, if they were both less than or equals to, we might have had a conflict. It might have not even have been a function. Could have failed the vertical line test. This ends at 1. That's strictly a strict inequality. It doesn't work at exactly 1. At exactly 1, you'd be using this piece right here. So those things should not overlap. They should be a complete partition, essentially, of the domain. Other questions so far? Okay, so the reason I'm bringing these piecewise functions to class today is, well, it's in the reading, so that's fair enough, but it's also in ALEKS, selected by the math department. And they selected stuff like this one. To me, this one is pretty tricky. So let's do this really carefully. Show all the steps on how this ought to go. And if you have more questions on plotting these, don't hesitate to ask about it. I'll be very happy to help out. So this is essentially a problem that you're going to see in ALEKS. Gives us a piecewise function, nothing too crazy because our goal is to graph that thing. And the ideas we used before are the same ideas we're about to use. It's all about those domains. So when we go to give the graph, the very, very first thing I want to do is emphasize those domains. So let me start by putting in vertical axis, horizontal axis. The interesting thing that happens is nearby 2. So I'll go 1, 2. I'm going to put a kind of a dashed line here. It's not a vertical asymptote. I'm just splitting the graph in half. So really, really light. Now, next thing I want to write in is the function f of x takes 2 forms depending on where you're at in the domain. If you're less than or equal to 2, that means you're on this side right here. So let's emphasize that by putting in a little bit of a bracket, right? Y equals -5x plus 3. So just in this window where you see the green bracket, not across the red dashed line, we're graphing that function. But then when you go across this dashed line, it turns into a whole new function, x minus 4. We'll do that one in blue. So to the right of 2, going to the right forever, we plot y equals x minus 4. So that's our setup so far. Does that make sense to folks on the organization portion of this? Okay, to me, this is the most important part because it can be a bit of a mess if you're plotting these kinds of functions. But if you organize, it helps out massively. Now, next thing I want to do is just plot these functions. You could use the slope and the intercept like we did before, but I'm going to try the different strategy of just selecting the point plotting method. So I'll put in scratch work, x here, and then with this one, y equals -5x plus 3, just to remind me which one I'm working on. I want to put in an easy value. 0 is still a nice and easy value. You could use +1 if you prefer, no harm done. I'll go with a 0 here. Plug in 0, you get -5 times 0 plus 3. So we're going to get a +3. And that tells us our first point is right here, 0, 3. That makes sense so far? Okay, now our domain extends all the way to 2. How do you plot the whole function all the way to this boundary right here? So next thing I need to put in is that 2. So 2 goes in. We're plugging 2 into that function, so it's -5 times 2 for a -10 plus 3. And we get a -7 out from that one. So at 2, we drop down to -7. Let me put in those tick marks. 1, 2, 3, 4, 5, 6, 7. Now here's the moment of truth. Here's why I feel like this is a really, really tricky topic. We have to make a big decision here. At -7, 2, coming from that table here, would we put a solid dot or an open dot? Anyone see which one we should throw in? Yeah, go ahead. Exactly. So that review work we did at the very top of this notes also supports this right here. So we'll use solid dot to end the last point on the graph. If it said strictly less than 2, right here, we would have used an open dot instead, because the function isn't valid right at 2. It's only going up to it. So here, we'll put in a solid dot right here. And now here's the hard step. The line goes this way with the arrowhead, but it doesn't go across the red border. Across the red border, it's a totally different function, x minus 4 instead. So it's a solid dot here, shooting off to the 11 in that direction. Almost there, folks. Does that make sense at the moment on getting this one through? Awesome. Next thing you have to plot is y equals x minus 4. So I would advise just do a brand new table for this one. Here's X, and now Y equals X minus 4. Now we need to put in key values for X. I love putting in a 0, but you absolutely can't this time. Does that make sense why? Awesome. If I put in a 0, we're using negative 5x plus 3. That's already plotted right here. So the most strategic value I could put in would be something at 2 or to the right. It turns out I need to put the 2 in itself. That's where the graph starts. So that's probably the best place for us to start. So 2 should go right here. Then I just need one other point. Let's put in a value of, say, 3. That will give us our right outputs. So now let's go and crank them out. 2 minus 4 for our first point gives us a negative 2. Then 3 minus 4 will give us a negative 1. And now back to our plot, where we have to be extremely, almost unfairly so, very, very careful about this one. Because of this, the first point we plot is with an open dot. Like these reserve exclamation marks, because it is tricky. So going back to blue, we use an open dot at 2, negative 2. So 2, negative 2, let me fix my graph a little bit. 2 ought to go here now. Then 2, negative 2 would be right here. But it has to be an open dot. If you put in solid, that means you're allowing 2 to be a point on the graph, but then this would be failing the vertical line test just immediately at that stage. So that's part of the function of why we have to pay all this attention to open and solid dots, extremely subtle. So there's 1 point in, we go to the next point, 3, negative 1. We're going to be right here. I'll make that a solid dot, it's just a point on the graph. And because this is a line, it just shoots off going that way. We just needed the 2 points. So that's a pretty busy graph, but anything here, the brackets with the function values, these tables here, all that's just the scratch work to obtain this. That's our answer. Any last questions, folks, on getting to this stage? Okay, well, congratulations, everyone. These notes were really long. And one thing that you might have noticed is part of the purpose of the notes in 3.1, 3.2 is the kind of review as well. It's the kind of things that we all need to know to be on the same page as we go through the rest of chapter 3. So last thing we want to discuss is domain and range, and if f is continuous. That's a brand new concept, but let's start with the nice stuff, domain. Anyone see what the domain should be on this particular problem? Exactly, all real numbers on this one. Even though there's an open circle here, you could plug in 2, you can plug in 3, everything larger, everything smaller, the arrows are going left forever and to the right forever. There's no gap of something missing on the horizontal axis. And that's our outputs right there. Range, well, that's trickier on this one, right? We need to find the minimum, the lowest point on the graph. Anyone spot the lowest point? Yeah, go ahead. Exactly. So that's where the range starts. The lowest output you can possibly get is this value at -7. But then all these other values are obtained, sometimes in multiple ways. Say 0 is obtained here and right here on the blue and the green curve. And it keeps on going upwards. So if there's no holes and it's always going upwards, it goes off to infinity right here. That makes sense, folks, on domain range for this one. Okay, last concept. And I'm not going to ask this question a lot. It's just kind of tacked on to one of your problems on Alex. It's asking, is this continuous? Continuity means no holes, no breaks in the graph, no jumps. You can draw the graph, never lifting up your pen. How do folks feel about it? Continuity here or no continuity? I agree. If there's a break, it's right there. We'll say not continuous. Not continuous. And the reason is for that there. If the blue curve was just drugged down So if the open circle overlapped with the solid one down here, there would have been no break and we would have said, yes, it's continuous. Sorry, question here?
So is that kind of where the horizontal line just goes in?
Absolutely, yes. For continuity, you're saying? Yeah, absolutely. Other questions or concepts so far? Or comments, I mean? Okay, sorry for going right to the minute, folks, but these were notes that I felt like I didn't want to shorten at all or try to rush through. On the next section notes, they're not always going to be as beefy as this, so it'll be a little bit more streamlined. Well, have a nice day, folks. If you do have questions, I'm here for just a few minutes and I'll be in room 220 for 4 to 5.